Hi, my name is Steve Feiner from Columbia University, and it's my pleasure to welcome you to IEEE VR virtual session 21 on comfort and workload. We have 5 great papers, and without any further ado, I'd like to introduce the very first one. It's on the effect of a foveated field of view restrictor on VR sickness. It'll be presented by Isaias Adanom, who will introduce his fellow authors.
Thank you.
Hi everyone,
This
my name is
paper,
Isaias Adhanom. I am a PhD student at the University of Nevada, Reno. Today
this
I'm
paper
going to
was written
present our
by
research work on the effect of a foveated field of view restrictor on VR sickness on behalf of my co-authors Nathan Navarro Griffin, Paul McNeilage, and Elka Fulmer. VR sickness or visually induced motion sickness is a sensation that is similar to traditional motion sickness that is specific to the domain of VR. It may involve several symptoms including nausea, sweating, headaches, disorientation, drowsiness, increased heart rate, and general discomfort. The severity of the symptoms may differ from person to person, but VR sickness is still considered a major hurdle for the large-scale adoption of VR. There are various theories that try to explain the cause of VR sickness. We will look at 3 popular theories here. The first theory is the eye movement theory. The eye movement theory suggests that rapid involuntary eye movements evoked by optical flow or visual patterns can innervate the vagal nerve in the brain and cause VR sickness. This happens when an image moves contrary to the user's expectations and unnatural eye motions or eye movements are required to keep the seen image stable on the retina. According to this theory, VR sickness can be reduced using a rest frame. A rest frame is a specific reference frame that the observer chooses and that appears to be stationary in the virtual environment. The second theory is the postural instability theory. This theory links VR sickness to a disruption of posture stability caused by the motion patterns of the visual stimulus of the virtual experience. According to this theory, repeated exposure to VR would allow users to better control posture and balance and in effect reduce VR sickness symptoms. The third theory is sensory conflict theory. This theory attributes VR sickness to a conflict between the visual, vestibular, and proprioceptive senses. This is the most widely accepted theory, and we will look at it in more detail in the coming slides. When we are walking naturally, our brain receives vestibular and proprioceptive signals in addition to optical flow signals. The vestibular signals are generated by the vestibular system as a result of the movement of our head when we walk. The proprioceptive signals are generated by the mechanosensory neurons located within our muscles, tendons, and joints. And the optical flow signals are generated by the receptors in our eyes. However, when we're moving in VR using a controller, we experience visual self-motion or vection, but there is no real physical movement, which means our brain does not receive the vestibular and proprioceptive signals that it receives when we are naturally walking. This leads to sensory conflict, which could cause vection-induced VR sickness. Vection-induced VR sickness can be alleviated by reducing or avoiding optical flow when moving in virtual environments. One popular locomotion technique that avoids optical flow is teleportation. Teleportation avoids optical flow generation by instantly translating the user's viewpoint from one point to another inside the virtual environment. However, despite its wide usage, teleportation is still considered to offer low presence, and the absence of optical flow can lead to spatial disorientation when using teleportation. And for multiplayer games, discontinuous avatar representations when using teleportation present a challenge for gameplay design, as it's impossible to follow or chase other players where they are jumping from one place to another in the virtual environment. Another widely used solution to reduce vection-induced VR sickness is reducing the field of view during locomotion. The solution relies on the physiological properties of the human eye. Our eyes consist of a central region that's used to see at a high resolution and a peripheral region that's primarily used to detect motion or optical flow in the field of view. So if we block the peripheral vision by applying an opaque texture with a transparent circular hole to the center of the user's field of view, as shown in the left side of the video, we can reduce vection-induced VR sickness. These restrictors can be implemented with users barely observing their presence in the field of view, and various studies have already found field of view restriction to be effective in reducing vection-induced VR sickness. Existing field of view restrictor implementations use a fixed restrictor where the effect is applied to the center of the head fixed field of view, which is only updated by the user's head gaze. In such case, peripheral motion stimulation is most optimally blocked when the head and eye gaze align. That's when the user is looking at the center of the head-mounted display. In the slide, we have denoted the user's center of gaze with the yellow circle and the peripheral vision that we want to block with the blue circle. This case shows the case where the restrictor and the peripheral region are aligning well. Let's see what happens when the user is not looking at the center of the HMD, which happens quite often. As you can see, the restrictor and the user's region of peripheral vision will not overlap in this case. This will have two negative consequences. First, the user's peripheral vision will be exposed to optical flow. Here in the video, it's denoted by the red region. And second, part of the restrictor may fall on the user's central vision, which would make the restrictor noticeable and could decrease the immersiveness of the virtual experience. So to solve these problems of existing field of view restrictors, we designed an FOV restrictor that moves with the user's eye gaze and assures that peripheral vision always remains blocked from optical flow. We named our FOV restrictor foveated FOV restrictor, and it's shown on the left side of the video. The foveated FOV restrictor is applied only when the user is moving in the virtual environment, which is similar to existing field of view restrictors. The effect is applied gradually so that it doesn't distract users, and its edges have linearly increasing opacity or feathering to make it less noticeable to the user. Once applied, the restrictor follows the user's eye gaze, and to avoid jerky movements, the restrictor's movements are smoothed using a smoothing algorithm. This foveated FOV restrictor has three advantages over the existing FOV restrictors. First, it assures that peripheral vision always remains blocked from the optical flow. Second, it makes it hard for a user to look at the restrictor itself or to notice the restrictor. And third, it allows the user to visually explore a large portion of the virtual environment during locomotion. So to evaluate the effectiveness of our foveated field of view restrictor, we investigated three research questions. The first question is, will the foveated field of view restrictor reduce VR sickness more than a fixed field of view restrictor? By fixed field of view restrictor here, we're referring to field of view restrictors that do not respond to the user's eye gaze. The second question is, will the foveated field of view restrictor allow for a more unrestricted view of the virtual environment than the fixed FOV restrictor? And the third question is, will a foveated field of view restrictor be less noticeable to users than a fixed field of view restrictor? To help us answer the research questions, we conducted a user study. Our user study had a mixed design with two independent variables. The first independent variable was FOV restriction, which are two levels, fixed FOV restriction and foveated FOV restriction. And the second independent variable was sex, or the participant's gender, which are two levels, men and women. We chose to look at sex as a factor because previous studies show VR sickness affects men and women differently. Our dependent variables were grouped into three categories: VR sickness, gaze dispersion, and noticeability. VR sickness was measured with the standard simulator sickness questionnaire and a discomfort score that users selected at specific time intervals during the experiment. Gaze dispersion was measured as a standard deviation of gaze points in the horizontal and vertical directions, and a third combined score was calculated from both these directions. Noticeability was measured using a participant observation questionnaire. 22 participants participated in our study. During the experiment sessions, participants were instructed to follow a set of waypoints at their own pace. Only one waypoint is shown at a time, starting with the first waypoint, and a set of 105 waypoints were added to the environment to guide the participants' movement in the virtual environment. And after every 5 waypoints, participants were asked to rate their level of discomfort from 0 to 10. With level 10 representing the highest level of discomfort. The virtual environment, which is shown in the slide, consists of an urban setting surrounded by lush green forests and winding dirt roads. The red dots in the figure represent the waypoints that were used in the study. After completing each session, participants were asked to fill out a simulator sickness questionnaire and a participant observation questionnaire to assess if they noticed the field of view restrictors during the experiment sessions. So it's time for the results. I'll first start by discussing the VR sickness results. We did not find a statistically significant difference between the fixed and foveated restrictors for VR sickness as measured using discomfort scores and SSQ scores. In general, the levels of observed VR sickness were very low. We did not detect a statistically significant difference in VR sickness between sexes either. Previous studies have shown that women are more likely to experience VR sickness. Therefore, the FOV restrictors used were likely successful in suppressing a higher VR sickness incidence in women. In our study, we did not have a baseline condition. That's a condition with no FOV restrictor, so no hard claims can be made about the effectiveness of a foveated field of view restrictor to reduce VR sickness. However, several studies have found FOV restrictors to be effective in reducing VR sickness. When it comes to gaze dispersion results, we did detect a statistically significant difference in gaze dispersion between the foveated and the head-fixed field of view restrictors, which indicates that participants covered a larger visual scan area when they were using the foveated field of view restrictor. This is shown on the left side of the image shown in the slides. This result points out an important benefit of using a foveated field of view restrictor over a head-fixed field of view restrictor. Users have more opportunity to look around without having to change the orientation of their head. This might allow for taking in more details of the virtual environment they are exploring, which could improve spatial navigation performance. Looking at differences in sex, we noticed that the effect of field of view restriction on gaze dispersion was especially evident in women, where we found significant difference in gaze dispersion in the horizontal, vertical, and combined measures, whereas for men, we did not detect any significant difference in the vertical gaze dispersion. This is an interesting finding, and we speculate that this could have been caused by the difference in spatial navigation behavior between men and women. Regarding noticeability, we did not find any statistically significant difference between FOV restrictor types. However, our noticeability scores were higher than previous studies that used the participant observation questionnaire. This could have been caused by the fact that we chose 55 degrees as the minimum size of our restrictor to match those found in popular VR experiences like Google Earth VR. So this size is highly effective in reducing VR sickness. It also makes the restrictor quite noticeable to participants. We could have explored using a larger minimum FOV for our restrictor, but this would likely have elicited lower scores for noticeability and higher VR sickness scores. So to conclude, we evaluated a foveated field of view restrictor, a restrictor rendered around the user's eye gaze location, and we evaluated the effectiveness of the field of view the foveated field of view restrictor on VR sickness, gaze behavior, and noticeability by comparing it to a head-fixed field of view restrictor. The results showed no significant difference in VR sickness or noticeability incidence between field of view restrictors. However, participants had a wider gaze dispersion, which indicates wider visual scan area when using the foveated field of view restrictor. Okay, that's it for me. Thank you. Thank you for your attention.
Thank you very much, Isaias, for a great talk. I want to remind folks out there in our virtual audience that there is a Slido for this session on which you can ask questions. I don't see any right now. And while we're waiting for questions to appear, I'm actually going to ask one. I really enjoyed this paper a lot. Of course, we were all at the mercy of the quality of the eye tracking that we can afford, and that's in many cases now being built into head-worn displays. My experience with these kinds of eye trackers is that ideally, if you put a little dot where it thinks I'm looking and I look around, the dot should be exactly at the center of my field of view. And of course, there's latency. And so I'm wondering if you noticed any effects of the latency. That is to say, it would seem to me that you would see a bit of that restrictor moving relative to your eyes rather than actually being exactly surrounding your center of your field of view.
Since what we observed was since edges of the restrictor fall on the peripheries of the user's retinas, the motions of the restrictor were not very visible to the users. However, the noticeability questionnaire actually does show we had high scores of noticeability, but that was the case for both the restrictors. Even for the fixed restrictor, it had almost similar scores. So the movement of the field of view restrictor, the foveated field of view restrictor, might not have been very noticeable. And as for the latency, we actually we added smooth dampening algorithm to smooth the movement. So that also adds a little bit of latency, but it was not very noticeable to users.
Right. Even if it's not noticeable, it seems to me that it's possible that it could influence the amount of VR sickness that someone is feeling. I think I actually have a question over here. I saw one appear and suddenly it's gone. Oh, okay. It somehow got approved. I'm not sure how that happened. So the question is, how did you determine the size of the field of view restrictors, and were they the same in both conditions?
They were the same in both conditions, and we chose the size of our field of view restrictor to be 55 degrees when it's applied, when at its maximum restriction. So it's gradually applied with respect to the speed of the user, his virtual speed in the virtual environment. So when he's moving at maximum speed, it's applied at the maximum restriction. It was 55 degrees. And we chose this based on restrictors applied on Google Earth VR and other popular VR experiences. So they choose a size that's around 55 degrees up to 60 degrees. So we chose that size. But other studies, including the study that was conducted by you, Stephen, I think you chose around 80 degrees for your restrictor.
Yes, we intentionally chose something to try to make it so people didn't notice it. Google obviously wanted you not to get sick, more important than having you not notice it. Yes, if you try turning that off in Google Earth VR, you will probably turn it back on very quickly. Let me see if I can ask one more question here. And I will ask this one. How did you calculate the number of participants in your experiment? And is a low number of participants maybe the reason for finding no differences?
We actually point that out as one of our as one of the limitations of our study. So we actually did have a very few number of users, and we have put it as something we want to do for the future. We want to try to calculate how many users we need to actually achieve the statistical power that we need and run a bigger study. But for this study, the number of users was low, and we have put that as a restriction, as one of the limitations of our paper.
Okay, thank you very much, Isaias. I'm going to applaud your work.
Thank you.
It's a pity not to hear. There should really be like an applause track, just so it sounds more reasonable. Okay, so I think at this point, I'm actually able to go to our next paper and speaker. And that next paper is on detecting system errors in virtual reality using EEG through error-related potentials. It's going to be presented by Hakim C. Mohammed, who will also introduce us to his fellow co-authors.
Okay, well, thank you a lot for the introduction, and thank you everyone for being here virtually in this session of VR 2020. My name is Hakim Si Mohammed, and I'm a postdoctoral researcher at INRIA Rennes, and I'm about to present to you the results of a collaboration that was undergone between INRIA and the Technical University of Graz. The title of the research is Detecting System Errors in Virtual Reality using EEG, which stands for electroencephalography through error-related potentials. In short, a very interesting property of the brain is that when users experience or witness an error during the interaction, a very specific brain pattern can be noticed in the electrical activity of the brain around the fronto-central region, something that looks similar to this behavior here. And this very specific pattern is known as the error-related potential, or in short, AKA the oh shit signal. Since it was first discovered in the early 90s, the error potentials, or ERPs, have been used in the scope of brain-computer interfaces, which are systems that enable to interact or send commands to a computer through the brain activity, the modulation of the brain activity. These systems are known to be very error-prone, and one of the most straightforward applications of the ERPs was to detect when a wrong command has been sent in order to automatically correct it. But the same goes also for the human-computer interaction community, which have seen in these error potentials potential implementation of the undo feature or Control Z function automatically. But ERPs also hold great promise in terms of applications in VR. So far, we are it's the very beginning of this exploration, and the first studies have tried to detect or to try to illustrate that some interaction errors elicit error potentials in VR. For instance, Yasmir et al. Developed a system where, thanks to a haptic arm here, a user could move a blue ball from the right to the left of the screen, but while being for some time occluded by this cylinder. In the correct trials, the ball would just go in the same level, but sometimes there would be like a shift into the height of the ball, which will be perceived as an error. And they showed that this, in fact, trigger error potentials. In the same time, Pedrao and al. Developed a system where they showed that, where they used error-related potentials as neurophysiological correlates of state of agency, where they've actually shown that violation of state of agency between a user and the virtual avatar actually did elicit error-related potential. So these error potentials were kind of an indicator of a violation of state of agency. More recently, Pizzetta and al. Also shown that observing errors in virtual reality do actually also elicit error-related potentials. But despite these promising applications, some limitations are still facing the current state of the art. In particular, we know that several types of errors can elicit error-related potentials. In particular, we have noticed that no previous study have tried to characterize the system errors happening in VR, or what is the effect of errors originating from the system on the user's brain. And moreover, um, in several cases, we have noticed that these ERPs were used as metrics of user experience in VR, like the work done by Pedro and al. On the state of agency. But no previous work was actually tackling the real-time detection of ERPs in VR, or detecting them in single trial or as soon as they happen. Facing these limitations, we have decided in this paper to try to answer two research questions. First, do system errors, and yet again, system errors, by system errors, we mean errors happening in VR and originating from the system and not from the users. So do these system errors elicit ERPs in VR? And then can we automatically detect these ERPs in VR? In order to answer these questions, we have designed an experiment where the general task consisted in a pick and place or drag and drop task, where the user was seated in front of a real table that was matched with a virtual table, and the users had to grab the object in the center, and it was a center out pick and place task where they had to drop it into the correct shape. Basically, three types of objects: the tetrahedra, the cylinder, and the parallelepiped. And obviously, each object was associated with the shape: the tetrahedra with the triangle, the cylinder for the circle, and so on. Later, we have designed 4 experimental conditions corresponding to the different errors that we wanted to test in VR. The first experimental condition, named the correct trials, was when the user actually grabs the object and drops it into the correct shape. In this case, the green or positive feedback is given by turning the shape into the correct color. And this is basically the main task and the baseline task. The first error that we wanted to study was the tracking error. And by tracking error, we wanted to study what happens when the tracking of the object that the user is actually manipulating is lost. In this situation, it is represented here by an object getting detached from the user's hand and frozen in the air. In this case, we've asked the user to remain still until the disappearing of the object in order to reduce muscle artifacts. And in this case, also no feedback is given, and this corresponds to the loss of tracking or the tracking errors. The second type of error that we studied is called the feedback error, or also known as the outcome error. And this corresponds to the situation where the feedback or the answer from the VR system do not match the expectation of the user. In this case, the user grabs the object, puts it into the correct shape, here the parallelepiped in the square, but still gets a negative or red feedback that do not match what the user is expecting. The last type of error that we wanted to study was what we call the background anomalies. We wanted to know what happens in the user's brain when they actually face rendering errors or background errors that often happen in VR, but that are not directly related to the task. In this case, we have implemented that under the form of a frame that was put on the table, and sometimes this frame would just flip and be put into an unrealistic situation by uncrossing the table. In general, our experiment consisted in 10 runs of 39 trials. Each run had 27 correct trials, 12 erroneous, split between 5 tracking errors, 5 feedback errors, and 2 background anomalies. In total, we have kept the number of erroneous trial as 1/3 of the total number of trials in each run. All the trials started by the appearance of an object, then the user has to grab the object, and in the tracking errors or the background anomalies, the error would happen in randomly between 25% and 75% of the total distance between the origin of the object and the destination. While the correct trials and the feedback error trials, the error would happen, or the positive feedback would happen at the end of the trial. Regarding the participants and apparatus, 15 people took part in our experiment, 7 female and 8 males, and they were all equipped with a HTC Vive as a virtual reality headset, and as the EEG headset, we use an ANT Neuro Ego Sport with 64 electrodes. One of the difficulty that we faced during the experiment was to actually associate these two headsets in a way that they do not disrupt the EEG signals, and which brings us to the collected data, which were basically the EEG data recorded through the trials, so the whole runs and the whole experiment, sampling at 512 Hertz. Now, regarding the results, we have analyzed every error or every kind of error separately. So regarding the analysis of tracking errors, the grand average brain activity of the user did actually show a pretty strong and clear ERP pattern that we can notice here, and the activity mostly happening in the frontal central region, confirming that actually tracking errors do trigger strong and clear error potentials, which was really encouraging. But when it comes to feedback errors, actually, we still do notice a very slight negativity happening right after the negative feedback, but we also notice the same behavior on the feedback, both positive and negative. So this is not really significantly discernible, but still encouraging. And one of the explanation was, or some possible hypothesis was, that the users did actually sometimes not pay attention to the result of the feedback because the task was too easy, and some of them reported going back to the center of the table waiting for a new object before even getting the feedback from the task. Or sometimes the task was too easy, and then even when getting a negative feedback, the users knew that they had done the task correctly, whereas the previous tracking error did generate some error potential, maybe because it was the most disruptive on the performing of the task, preventing them from accomplishing it. And now, regarding the analysis of the background anomalies, the actual brain activity, the display of the brain activity across the users, the grand average, did not seem to have generated any specific pattern between the correct trials and the background anomalies trial. So our hypothesis is that either the users did not notice the happening of the error, or maybe it was just completely unrelated to the task. So still further investigation has to be done, but no ERPs were generated in our case by the background anomalies. Regarding the second research question that we had on the automatic detection of these error potentials, we have decided to study the possibility to classify between correct trials or pieces of EEG containing correct trials and error trials in single trial. For that, we have taken the trials of 250 milliseconds starting right after the event onset. So these are pieces of EEG. And as features, we have used the amplitude of the frontal-central electrode, the FCZ, which corresponds to the electrode with most of the activities undergone. And we have trained linear discriminant analysis classifier, RDA classifiers, in order to classify between correct trials and error trials in the two cases. First, in terms of classification accuracy of tracking errors, we have noticed a pretty high, actually, classification accuracy, around 85%, with also a high specificity and sensitivity, suggesting that it is, yes, possible to detect these error potential happening after tracking errors in single trial. However, regarding the classification results of the feedback errors, we do not notice any above chance level results. So 60% is around chance level is not significant enough. So it's much more difficult to detect or to discriminate between correct feedback and negative feedback in these trials. Now, regarding these results, regarding the first question about, do system errors in VR trigger eroded potential? The short answer would be yes, at least for the ERPs generated by tracking errors. As we have seen, these generated pretty strong and clear ERPs right after the error, but background anomaly, for instance, did not seem to elicit error potentials. So maybe still some work is needed in order to be able to notice what is happening there and why some errors are possible to detect and others not. Maybe the effect of the errors on the interaction process. And regarding the second question of the automatic detection of ERPs in VR, the tracking errors, actually, to discriminate between trials containing tracking errors and correct trials, have enabled pretty high single trial classification accuracy. But it was much more difficult to classify between correct and erroneous feedback, as we have seen. But interestingly, we have noticed in our when looking at the results of the subjects individually, we have noticed that for 5 subjects among the 15 ones, the classification accuracy was still above chance level, which is encouraging. But we could not conclude anything yet, because we still need to do further studies in order to discriminate what's happening there and why for some people it's possible and not for others. In summary, we have conducted a user study to investigate the presence of ERPs when facing different system errors usually happening in VR. So frequent system errors generated by the VR system in VR, the tracking errors, the feedback errors, and the background anomalies. And the main takeaway message from this paper, from our results, is that actually the tracking errors, which were the most disruptive and maybe very frequent in VR, did generate strong and classifiable ERPs in single trial. However, there is still room for more work. In particular, we would like to design techniques in order to automatically and especially asynchronously detect error potentials in VR. Because even though we have conducted single trial classification, meaning taking each trial as a whole, we still use the information about when the error happened. If we want to have something that works in real time, the next step would be to go for asynchronous, meaning that we are able to detect at any time between error potentials and correct trials in order to detect them on the go and whenever they happen. And also, we would like to explore new applications of the possible detection of ERPs in VR. For example, we would think about the Control Z in VR, canceling the last command sent by the user, or maybe to flag the system, to flag the VR experiments while users are conducting their VR experiments, just to flag when they notice error happening, which would allow, for instance, to better study what are the elements that break the sense of presence in VR. Well, this basically concludes my talk. I would like again to thank you all for your very kind attention, and thank all my co-authors, Catarina Lopez-Diaz, Maria Duarte, Fernanda Guelaguet, Camille Jeunet, Jerry Cazier, Gernot Müller-Putz, Anatole Cuyer, and Renaud Cher for their help and their support in this work. Thank you very much.
Thank you very much, Hakeem. That was a great talk, and it looks like we have a bunch of questions as well. So let me switch over to them and see if I can ask them. And the first one that we have over here is from Rodrigo, who asks that you explain why you decided to use an LDA classifier.
Well, as I've mentioned, thanks for the question. Actually, the very first goal of the paper was to try to see whether we could elicit the error potential, these ERPs, considering different error happening in VR. So we were not specifically interested into how we could design or classify those. So we basically used some of the most state-of-the-art techniques for detecting error potentials. So it's not something novel here. Other papers had claimed pretty good results using LDA, and we as well, but probably maybe working on new or other techniques for asynchronous detection may also help improve the results. But it's something that is very frequent in the state of the art.
Okay, thank you. Let's see, we have another question over here from Alec Moore, who asks if the activity was more difficult to reliably perform correctly, such as the target zones being more ambiguous or overlapping, would you anticipate the feedback error potentials to be more pronounced, like if the user blamed themselves?
I'm not sure I understood completely the question, but if it's about the complexity of the task, then yes, that's only my own hypothesis. I hypothesize that if, and this is something we have discussed about in our team with the authors. So we hypothesize that if the task was maybe more complex to perform, and then the feedback maybe would have like an impact on the user for him to know exactly if they performed correctly or not, then maybe yes, that would have a stronger impact and maybe clearer error potential in the brain activity. So one of the reasons that may explain why the feedback errors were less pronounced in terms of ERPs than the tracking errors, our hypothesis is that maybe the user did not need actually the feedback to know if it was correct or not. So yeah, definitely, maybe by complexifying the task or studying more complex tasks, this would work.
Okay, one more question from Daniel. Were users informed in advance that they would be encountering multiple system errors? And does advanced knowledge tend to affect the detection of ERPs?
Well, thank you very much for the question. This is indeed a very interesting question. So no, we did not. We specifically did not tell the users that they would be encountering errors. So we just asked them to perform the task, but just inform that okay, the system was not perfect, and we told them that okay, there might be errors happening, and that they should still behave. So, in fact, we told them that errors may happen, and we specifically asked them how to behave when this error happens. For instance, with the tracking errors, asking them not to go back to the object and waiting remain still until the end of the trial. But we did not specifically tell them that the goal of the experiment was to actually study the error potentials. So for them, it was just like, okay, the errors happening from the system.
Okay, and one more quick question from Catherine Mimnoff. Sorry if I botched your name. Did you collect eye blink data from an EOG sensor? How did you remove blinks, saccades, and other artifacts? If not, did blinks and other artifacts have an impact on the signals if the HMD was in the way?
Yeah, absolutely. So thank you again for the question. Yes, definitely, and this is something we stressed out in our paper. Muscle artifacts and especially eye blinks might be of great disruption, especially for the error potentials. So we did not specifically remove the artifacts from the data, so we did not clean the data. But we performed statistical tests that are detailed on the paper on selecting on trying to detect which are the trials that contain artifacts, and then trying to remove them using kurtosis analysis, for example.
Okay, thank you very much, Hakeem.
Thank you very much.
Really appreciate the talk.
Thanks.
And now we go to our third talk, which is on introducing mental workload assessment for the design of virtual reality training scenarios. It'll be presented by Tiffany Dong, who will present her co-authors.
Okay. So am I live now? Okay, cool. So hello everyone, and thanks for the introduction. So I'm going to present you our work, which was done in collaboration with Fernand Guelaguet, Nicolas Martin, and Anatole Cuyer. So I'm going to present you how to introduce mental workload assessment for the design of VR training scenarios. So as most of you know, VR is very convenient because it engages the user in the virtual world, and it's especially useful in the training field because users can do it at home, and most of the time it's cheap, safe, and controlled compared to more traditional methods. So as you saw in the title, we are especially interested in studying mental workload. So mental workload is a cognitive state which is quite well studied in VR, as you could see during the multiple sessions during the conference, and it's especially studied in the training field because overloaded or underloaded users can lead to unsafe situations or to inappropriate trainings. So that's a metric we want to control in VR trainings. So in VR, the scenarios are most of the time prescripted. So you have sequences of events, and those events are going to be triggered depending on users' actions and choices. And since VR environments are most of the time very complex, with a lot of interactions, avatars, and animated agents, there have been some tools which have been developed to simplify their design using, for example, animated agents, so for example, Petronet representations that you can see on the left, or state machines that you can see on the right. So the issue here is that the scenarios are most of the time based on narrative and interaction requirements, and they don't really take into account the user psychological states, and most especially the user's mental workload, which is our target of interest today. So sometimes, if you only take into account the narrative and interaction requirements, so the users can end up getting bored as on the left, or overloaded as on the right. So there have been some studies which adapted the task difficulty based on users' performances, which was the case, for instance, for Parsons and Rainbow studies. And there have been some studies which adapted the task difficulty based on users' physiological signals, which was the case, for instance, for the whole study. So performances and physiological signals have been found to be correlated to users' mental workload, but they are not fully representative of it. But what's important here is the fact that some studies tried to adapt the training scenarios or just a scenario based on some metrics which were related to users' mental workload. But the issue here is that the adaptation was done in a single task context and not in a complex one, such as on the pictures here, with multiple parallel tasks. So it is quite understandable because when you have a lot of tasks, you don't really know which task you want to adapt in its difficulty or which task you want to automatize based on users' mental workload. So the research question we are going to tackle today is the following. How do we introduce mental workload in complex training scenarios? So our objective is the following. We want to introduce mental workload in the design of VR complex training scenarios involving multiple parallel tasks. So we proposed a very straightforward approach using 3 steps. First, the state machine generations. So we want to identify first the different task difficulty levels, and we want to associate these difficulty levels together to form the states of the state machine. Then we want to assess the mental workload inside each state of the state machines. And finally, we want to use this mental workload assessment and the state machine to generate scenarios which are going to modulate mental workload over time. So we conducted a user study to illustrate the approach using a VR flight simulators. And what we did was we adapted the MATB2, which is a software developed by the NASA to study human performance in a multitask context in VR. So on the left, you can see the original MATB2, and on the right, you can see the adaptation we made in VR. So we only adapted 3 tasks of the MATB2, and so we adapted the tracking task or piloting task, the communication task or radio task, and finally the resource management task or fluid task. And here you can see our experimental setup. So as you can see, the user is piloting the aircraft using a joystick, and he can only orientate the aircraft and can't really accelerate nor decelerate. And as you can see, he's holding a Vive controller with his left hand, which can be used to interact with the VR buttons. So I'm going to give a little bit more details about the task, the objective, and the difficulty level, starting with the piloting task. So we ask users to follow the green line as closely as possible during the experiment. So we had 3 difficulty levels, and we changed the difficulty by changing the flying speed and the number of visible circles the user could see at the time. For the radio task, we had 2 difficulty levels, so deactivated and activated. And when the task was activated, the user was asked by a voice in the headset to turn the radio on a specific frequency. So sometimes the message targeted the user, and sometimes it did not. For the fluid task, we also had 2 difficulty levels, so deactivated and activated. And when the task was activated, the user was asked to maintain the 2 tanks level at the top in the blue zone. So when the task was activated, the 2 tanks level started to decrease, and the user could use the 8 pump buttons, which are numbered from 1 to 8, to try to maintain the tanks level in the appropriate zone. So here you can see the interaction. So what we want to do now is to represent all of the possible task configurations using a state machine. Therefore, a state inside the state machine is going to be a task level configurations. So we are going to use the following notations. So the first digit is going to be the piloting difficulty level. The second digit is going to be the radio task difficulty level. And the third digit is going to be the fluid task difficulty level. So it gives us the following state machine with 12 states. And here the transitions were added between the states, differing in only 1 level of difficulty. So this is supposed to be the easiest task level configurations, and this is supposed to be the hardest task configurations. So now going to the second step of our approach. So we generated the state machine, and now what we want to do is to collect mental workload data inside each state of the state machines. So we want to determine how much mental workload each of these task configurations are going to induce to users in average. So we had 38 participants, and we made them traverse all of the state machine in a randomized order using only consecutive states. So we collected several types of measures of mental workload, but today during this presentation, we are just going to focus on the subjective mental workload via the ISA scale. So we ask users during the experiments to rate their mental workload using 5 different ratings via the ISA scale. So 1 is supposed to be the lowest mental workload level, which means that the user is getting a little bit bored and that he has little or nothing to do. And 5 is supposed to be the highest mental workload level, which means that the user is struggling to complete the task. So here is the way we ask users to report their mental workload, and we ask them to report their mental workload multiple times per state and why they were doing all of the other tasks. So we also recorded performance and behavioral measures, and we had interesting results, but we won't detail them today. You can, of course, find more detail in the paper. So here are the results we obtained, and you can only see the result for the subjective mental workload or ISA level here. So on the left, you can see the effect of the piloting task difficulty on the subjective mental workload or ISA. And on the right, you can see the effect of the different task combinations on the ISA. So what I wanted to point out is the fact that the fluid task induced more mental workloads than the radio task. And we also had an interaction effect between the thread task and the piloting task difficulty. So it can be explained by many things. So maybe the thread task was just more difficult than the radio task, or maybe following Weekend's theory, it stimulated the same pools of cognitive resources on the piloting task, so visuomotor resources, contrary to the radio task, which was more auditory cognitive resources. So maybe that's the reason why it induced more cognitive mental workload levels on the radio task when associated to the piloting task. So this is our resulting mental workload level map. And as you can see, the task easiest level configuration induced the lowest ISA level, and the task most difficult level configuration induced the highest ISA level. So we obtained here quite a nice gradient of mental workload level, and we were very happy about it because in such type of experiments, sometimes it can be quite a strong challenge to ensure an equal distributions of workload values. So here the distributions of workload values was surprisingly good. So now we finish the data assessment and we have a map of the mental workload each state induced to user in average. We can now design some scenarios. So going now into the third part of our approach, we designed 3 different scenarios which can be envisaged in a piloting training context. So for the first scenario, we wanted users to be in an optimal mental workload state alone. So we also wanted them to try out different task combinations, but we wanted them to be at ISA equals 3. So we chose the 5 states which had the ISA level the closest to 3 in the state machine to design this scenario. In the second scenario, we wanted users to experience a sudden increase of mental workload level in the end. So it can be, for example, a scenario where the trainer wants to see how users are going to react to surprising situations. And for the third scenario, we wanted it to increase the user's mental workload progressively. So it can be a scenario where we want to evaluate, for example, the user's performance to an increasingly pressuring situation. So going now into our second experiment. So our objective here is to assess the effect of the training scenario generated using our approach on the user's mental workload. So just a quick reminder, in the first experiment, we made users traverse a state machine in a randomized order and we assessed their mental workload levels. And in this experiment, we have 3 scenarios and we made different users, traverse some parts of the state machine in a fixed order. And what we expect is not to see any significant effect between this experiment and the first one, even if the experimental design is very different. So we want the 3 scenarios we designed to induce the expected mental workload progressions over time based on the first experiment data. So we had 14 participants, and they all did the 3 scenarios in a counterbalanced order, except for the 2 last ones who did them in a randomized order. So we collected the same data as in the first experiment, plus some subjective measures about how they perceive the difficulty progression after the scenario they did or after all 3 scenarios. But we are just going to focus here on the ISA. And so on the subjective mental workload we recorded during the scenarios. So here on the x-axis, you can see the state of the state machine, which were used to design the 3 scenarios. And on the y-axis, you can see the subjective mental workload level or ISA level. So displayed here, you can only see the result for the first experiment when the users traversed all of the state machine in a randomized order. And now in purple, you can see the result for the second experiment when the user traversed part of the state machine in a fixed order. So as you can see, we didn't find any significant effect between the first experiment and the second one. And that's a good news because it means that even if we had very different experimental design and different group of participants, we managed to induce the same progressions of mental workload over time. And it means that the approach somehow worked. So we proposed an approach to introduce mental workload in VR training scenarios using 3 steps. So first, the state machine generations, where we tried to represent all of the possible task-based configurations, and then the mental workload assessment. So we assessed mental workload data inside each state of the state machine, and finally, the scenario generations using the mental workload assessment. So we conducted 2 user studies, a first experiment to assess the mental workload data in the generated state machines, and a second experiment to make sure that the scenario we designed using the assessed data during the first experiment induced the expected mental workload progressions over time. So even if the experimental design was different. So it validated our approach and we learned some lessons during these experiments. So first, the ISA scale is a good way to assess mental workload in real time. We just have to make sure that the scale is proposed to users in the same way between the different tested conditions. And we also found out that the thread task induced more mental workloads on the radio task, but we just discussed it a little bit earlier. So there are some limits in our paper. So first, the data assessment part can be quite time consuming, especially if you have a lot of difficulty level. So we proposed some simplification in our paper by selecting, for example, some specific states in which you want to assess the mental workload data, and then you can somehow estimate the mental workload in between. And we didn't really take into account the transition effects during the data assessment part, which might have to be taken into account in other contexts. So for future works, since we are now able to control somehow how we can induce mental workload to users, it could be quite interesting to assess the effect of mental workload modulations on other metrics, such as behavioral or physiological measure, for example. And it could be very interesting too to try to adapt the scenarios based on users' mental workload in real time, since we have structured our training environment. Also, it could be quite interesting too to try to extend the approach to affective states, such as emotions, for example, in other fields, to try to modulate users' emotions over time and to see if it improves user experience or not. So thank you for your attention. And if you have any question, I'll be glad to try to answer them.
Okay, thank you very much, Tiffany. It was a great talk. Let's see if we have any questions coming in over here. And it looks like I don't see any, so I am going to ask one in that case. And that's that here you have people interactively, while they're performing the task, trying to subjectively rate their workload. And I was wondering if, based on those subjective ratings and perhaps tracking lots of different things that were happening during the sessions, you have been able to think about ways in which you might be able to correlate, for example, things coming in from EEG or eye tracking or other signals with that subjective mental workload, so you wouldn't have to actually ask that question?
Yes, that's a very, very good question. So I'm not just going to spoil too much the future works, but exactly that's something which we are very interested in studying. So the either so the subjective mental workload report can be a little bit intrusive. So it would be a good way to try to record mental workload using just objective measures. And the fact that we are using subjective measures during the experiment can be a good way to try to correlate so objective measures to recognize mental workload data using the report, self-report. But yes, we didn't. I'm just not going to spoil out the future works. So yes.
Okay.
I don't know if it answers the questions.
Well, let's ask one more question,
Yes.
and that's the question that perhaps task location had an effect on its difficulty. Maybe the radio required more time with the eyes down than the other tasks.
Oh yes, that's very interesting. So what we tried out was to place the user so he could see approximately all of the tasks. But yes, he had to look down to look at the radio task. So we didn't find actually any effect on the task performance on the reaction time for the radio task between the different piloting difficulties. But how do we say? It's possible that the radio task induced somehow more mental workload when the user had to look down. But he didn't have to look down all the time because he just had to hear the voice and to see if the message targeted him or not. And if it targeted him, he just had to look down at this moment to change the radio frequency, but not all the time. So yes, it's possible that when you had to change the radio frequency, it induced more mental workload just at this point and not when you didn't have to do anything so for the radio task.
Okay, thank you very much, Tiffany.
Thank you.
Okay, so our next talk is on comparative evaluation of the effects of motion control on cyber sickness in immersive virtual environments. It'll be presented by Roshan Venkatakrishnan, who will also introduce his fellow co-authors.
Hey everybody, thanks for tuning into this talk on the comparative evaluation of the effects of motion control on cyber sickness in immersive virtual environments. Currently, VR is used in a multitude of settings spanning education, rehabilitation and therapy, training, and military and defense settings, medical scenarios, apart from just the entertainment settings. However, VR is yet to become a ubiquitous computing technology like smartphones, which almost everyone nowadays uses. So VR isn't currently where it needs to be, uh, where everybody is using VR for collaboration, work, and recreation. So what is it that's stopping or preventing VR from being widely adopted? The biggest hurdle that VR is seeing is cyber sickness. This begs the question, what is cyber sickness? Cyber sickness can be thought of as a malady or a feeling of discomfort that often accompanies VR experiences. It produces symptoms similar to that of motion sickness, such as nausea, eye strain, oculomotor discomfort, dizziness, sweating, amongst other things. So, cyber sickness is generally associated whenever there's travel in these virtual environments. With this in mind, we wanted to understand how cyber sickness can be alleviated. And specifically, we wanted to focus our attention on vehicular or virtual motion control and how this affects cyber sickness. With this research goal in mind, we thought this would provide you some context into understanding how we went about reviewing the literature. So we first looked at the factors that influence cyber sickness. So several factors have been shown to influence cyber sickness, such as the VR experience, the duration or the time in which one spends in VR, the field of view, and the speed of travel. Uh, Recently, work has shown that the addition of latency jitter can increase cyber sickness. Also, dynamic blurring of visual stimuli on the retina can reduce sickness. As such, the travel techniques have evolved to improve the user experience and reduce sickness. Teleportation, operationalized by a term jumping, has been shown to induce lesser sickness than steering. Jumping into control and cyber sickness, it has been shown that having control over self-motion stimuli generally renders people less susceptible to motion and cyber sickness. And this has been shown in the real world, desktop virtual environments, and even virtual avatars in virtual environments. In one such study by Dong et al. In 2011, drivers were found to be less sick than passengers when they played a Forza 2 racing game on an Xbox 360. So to answer these research questions, we developed a immersive virtual environment, which was a virtual city spanning 120 city blocks. It contained realistically scaled skyscrapers, apartment complexes, restaurants, and buildings sparse throughout the city. Apart from this, street signs, speed limit signs, trees, and trash cans were placed throughout the city in order to make the city more convincing of itself being a realistic urban setting. So we designed the layout of the city to include a variety of structural buildings, including tall and short buildings and landmarks that were evenly distributed throughout the city. There were broad and narrow streets and highways and intersections throughout the city. For the entire city, we employed a sort of concentric pattern in order to provide a uniform optic flow when participants travel through the city. Some of the landmarks can be seen in this picture, and they were salient and distinguishable from the rest of the structures in the city. So the apparatus that we devised was a wooden platform on which a real-world Subaru car seat was mounted on this platform. Uh, a Logitech steering wheel, along with an accelerator and brake pedals, were attached in order to provide a VR experience, along with a HTC Vive controller that was strapped on to the arms of the participant in order to provide a gender match scale self-avatar. As you can see, this is a picture of the first-person point of view of the immersive virtual driving simulation. So the specific research question that we were interested in is, how does the presence or absence of control in an HMD-based VR driving simulation affect the onset and severity of cyber sickness? And for this, we designed a study, more specifically a between-subject study in which we manipulated the control between three conditions, namely driving condition, a yoke pair condition, and an autonomous car condition. The latter two, that is the autonomous and the yoke pair condition, had participants behave as passengers, while in the driving condition, participants were allowed to drive the vehicle. Now, the driving condition and the yoke pair condition formed a matched pair in that the vehicular motion stimuli experienced by participants in both these conditions were identical, and this can be understood by the following video.
In the driver condition, the participant had full control of the car and could drive around a city as he or she pleased. Their task was to find a landmark presented on the car screen. Once the participant found a landmark, a new one was presented. The task remained the same across all conditions. In the other two conditions, the participant was driven around in a self-driving car with different behaviors. The autonomous car accelerated and decelerated at a constant rate and followed all traffic rules and regulations. Whereas, the yoke pair car behavior was a playback of one of the driver's trajectory from the driving condition.
We had a search task in order to have participants locate landmarks that were presented on the GPS screen of the car. The reason behind having the search task was to direct participants' attention outside the vehicle into objects that were not stationary inside the vehicle. And another reason was we wanted to keep the users engaged and in the simulation for longer. We had about 63 participants, 21 allotted per condition. 68% of our participants were males with an average age of about 24 years. And we noticed that VR experience did not significantly differ across conditions. For the procedure, participants, after they consented to participate in the study, were administered a demographic survey in which we asked them normal demographic questions like their age, race, gender, apart from their VR experience and other questions. Then we administered a simulator sickness questionnaire developed by Kennedy et al. In order to get a baseline measure of how sick participants were before the simulation. So the first 42 participants were randomly assigned to one of two conditions, that is the driving or the autonomous condition, and then the last 21 participants were assigned to the yoke pair condition. The reason behind doing this was because we needed all the driving trajectories to be recorded in order to randomly assign participants in the yoke pair condition to each and every driving condition. Essentially, each participant that went through a driving condition was matched with a yoke pair participant that went through the same trajectory. Now, we described the procedure for a participant in the driving condition. So participants were first briefed on the task they had to perform in the environment, after which the Empatica E4 wristwatch was strapped onto their hand in order to gauge and measure levels of skin conductance. After this, participants' arm lengths were measured in order to provide a realistic gender-matched scaled self-avatar. After this, participants began the driving simulation in which they drove around the city and were tasked with finding the landmarks that were presented on the screen. Participants could quit at any point they wanted, or at the end of 30 minutes, if they were still continuing, they were asked to discontinue because the maximum allotted time was 30 minutes. After the simulation, participants were administered the simulator sickness questionnaire in order to gauge their levels of sickness induced through the simulation. A similar procedure was employed for participants in the other two conditions, with the only difference being that they were not driving the cars, but they were passengers in a self-driving car. Based on a review of the literature, we developed the following hypotheses. We hypothesized that participants in the driving condition would exhibit lower levels of cyber sickness when compared to the other conditions. In our second hypothesis, we hypothesized that participants in the driving condition would spend more time in the simulation when compared to the other conditions. And finally, we hypothesized that participants in the yoke pair condition would get sick at an accelerated rate as compared to the other conditions. With respect to the results, our analysis of the data revealed that drivers experienced more sickness than their yoke pairs. We observed no significant differences between the autonomous condition and the other two conditions. The graph on the right shows the average SSQ scores, or the simulator sickness scores, broken down by condition. Breaking down cyber sickness into its subdimension, that is nausea, the data revealed that yoke pair participants had significantly lower nausea scores than the driving condition. Similarly, participants in the yoke condition had significantly lower nausea scores than the autonomous condition. And the graph on the right shows the average SSQ nausea scores broken down by condition. And when we went into the subdimension of disorientation, uh, our analysis of the data revealed that participants in the yoke condition had significantly lower disorientation scores than participants in the driving condition. They also reported marginally lower scores than those in the autonomous condition. So the graph on the right here shows the average SSQ disorientation scores moderated by condition. With respect to the results concerning the duration in the simulation, we found no significant effects of condition on the time spent in the simulation. However, there was a main effect of motion sickness susceptibility such that participants that were more susceptible to motion sickness spent less time in the simulation. We operationalized rate of change of cybersickness on two different fronts. The first one was the periodic self-comfort ratings, where participants reported their comfort levels periodically during the simulation every 3 minutes on a scale from 1 to 10, where 1 was the least comfortable and 10 was the most comfortable. And on the second front, we used skin conductance levels, or also known as electrodermal activity, by having an Empatica E4 watch that would measure this, and this would operationalize as our rate of change of cybersickness measure. So with respect to the results concerning periodic comfort scores, we found no main effect of condition on the rate of change of cybersickness. However, there was a significant main effect of condition and interval. Individuals in the driving condition became less comfortable at a rate faster than individuals in the yoke pair condition, or than their yoke pair counterparts. The graph on the right shows the effect of the interval on comfort ratings moderated by condition. Here, the interval represents the time between the periodic comfort measure. So this was measured every 3 minutes during the simulation. Going into the skin conductance levels, there were no significant differences between the conditions as revealed by the SEL scores. The graph on the right shows the predicted effect of the interval on the EDA data, moderated by condition. We also collected data on head rotation operationalized as the average yaw experience per minute and the average roll experience per minute. Both condition and time were significant predictors of the average yaw per minute. So drivers rotated their heads more, operationalized by the average yaw and roll per minute. The graph on the right here shows the effect of the interval on the average yaw per minute moderated by condition. So it's broken down by condition as driver, autonomous, and yoked. So what can we take away from our results? The first thing is it goes against the trends observed from previous research where drivers generally get less sick. However, in our study, drivers got more sick. So this could be attributed to a lack of inertial feedback upon the exertion of control, and this could have caused a mismatch in vestibular sensory expectations. Drivers could have had a larger degree of mismatched sensory motor expectations than their yoke pair counterparts, causing them to get more sick. So this refuted our first hypothesis, in which we hypothesized that participants in the driving condition would exhibit lower levels of sickness when compared to the other conditions. With respect to head rotation, drivers rotated their heads more, operationalized by average yaw and roll per minute. Now this could be a consequence of having to drive around the environment, having to abide by the rules of traffic, keeping in line with the speeds and lane changing, and essentially abiding by the rules that were enforced in the city. The increased head rotation and possible differences in the optic flow experienced by participants may help explain why drivers get more sick than their yoke pair counterparts. Now, with respect to the duration of the virtual experience, there were no differences between drivers and passengers in the amount of time that they endured the simulation. So participants who stayed in the simulation for longer exhibited lower levels of sickness. This could be because participants that spend longer time in the simulation do so only because they are more comfortable and less sick in the first place. Or they could have possibly adapted to the environment or to the experience. So Our hypothesis that participants in the driving condition would spend more time in the simulation when compared to the other conditions was countered by our results here. With respect to the rate of change of cyber sickness, there was an interaction effect between the condition and the time interval. So drivers became less comfortable at a rate faster than their yoke pairs. Analysis of the SCL data revealed no differences between these conditions. So our third hypothesis, in which we expected participants in the yoke pair condition to get sick at an accelerated rate compared to other conditions, was refuted. So what does this all mean? Having control over one's motion could lead to higher levels of sickness. So just giving or simply providing control need not necessarily alleviate cyber sickness, but could consequentially do more bad than good in that it could worsen the symptoms. So as a VR developer or as a simulation designer and VR researcher, it is very important to consider the fidelity of the travel metaphor. More specifically, it is important in considering how faithful the simulation is in replicating the feedback obtained in response to the control inputs and control that is exerted by participants or users. Additionally, it's important to consider the accuracy in matching the expectations drawn from real-world experiences. So it could be that participants that were drivers in our study come in with some sort of an expectation because they know how a real car works, but the lack of inertial feedback or the lack of realistic fidelity of our driving simulation did not meet their expectations, and this could be a reason why they got more sick. In hindsight, looking at the limitations of our study, factors such as the cognitive load and the engagement during the VR experience could have differed across conditions. We employed a search task to keep participants in the simulation for a longer duration and to keep them engaged throughout the experience. But this may have come at the cost of rendering drivers with a higher overall workload when compared to passengers. So we acknowledge these limitations and would like to address these limitations in future studies. Finally, I'd like to thank all the participants and all my collaborators and my advisor, Dr. Babu, for guiding us throughout this project and making it a success. Thank you, and I'll now open the floor to questions.
Thank you very much for a great talk, Roshan. We indeed have lots of questions coming in from the audience. And so the first one I'm going to choose over here is whether you checked if participants in the yoke condition showed different behavior apart from head rotation. Did they maybe close their eyes or stop paying attention, which may have led to reduced cyber sickness? And I'm going to add to that of course, the driver, unlike a lot of previous experiments with drivers versus passengers in old-fashioned cars, they really had to do a lot of looking inside the car, particularly at that stable GPS system and interacting with it. So the question is whether that might have had something to do with this perhaps unexpected result.
Okay, great question. So we did ask in the debriefing session. We did ask participants if they were, closing their eyes or looking at the periphery, or what they were doing as they were, engaging in the simulation. And we found no such thing that surfaced on top saying they were closing their eyes. So as far as that question goes, we did not observe anything as to whether participants were closing their eyes, because we did ask them and none of them mentioned that. So, and the second question you asked was looking inside the car versus looking outside. We did not have eye tracking in this study, but we do have some simulation data that we have to dig a little bit more deeper to see if participants were looking inside compared to looking outside, and to see if that might have played an effect in the results.
Because of course they did have to look at the GPS, right?
Yeah, they had to look at the GPS to observe voluntarily, to look at the landmark that they had to find when the car was traversing the city. So they would look at the GPS and then look outside where the car is moving around the city, and then look for the landmark. So
right. Yeah. Okay, so we have another question over here, and that was, how long did the cyber sickness last after simulation? Hours, days, both women and men? And that's asked by Carlos.
That's a great question. So most participants, when they get sick, it lasts for a couple of hours. We did have one participant that did throw up. That was not really fun. Apart from that, only a couple of participants did contact me the same night of the study. So I would say a maximum of about 5 hours was the time that we were able to see the symptoms last.
And one more question from Alex Rake, and that's whether it can be ruled out that participants in the yoked group were simply less prone to simulator sickness. So how did you know that the groups actually were comparable?
We did collect data on the susceptibility to motion sickness, and we noticed no significant differences across conditions. So so we cannot say that participants in the yoke condition were more prone to sickness.
Okay, thank you very much, Roshan.
Yep.
Okay. And I'm noticing that to set us up for the next talk, your name is actually your brother's name over there.
Yeah, I'll say you could say hello to him.
So he's going to take over in a couple of seconds. Yeah. And that next paper is on a structural equation modeling approach to understand the relationship between control, cyber sickness, and presence in virtual reality, being presented by Rohith Venkatakrishnan. I'm sorry.
Hello, everyone. This is also a pre-recorded video, so I'm just going to mute my video and audio.
Everyone, welcome to this talk titled A Structural Equation Modeling Approach to Understand the Relationship Between Control, Cyber Sickness, and Presence in Virtual Reality. So before I get into the meat of the matter here, I thought I'd provide you a preamble as to what you can expect to take away from watching this talk. So you can expect to understand how and why control is important in immersive virtual experiences. And by control, I mean virtual motion control or control over your travel in the virtual environment. And you can also expect to understand the relationship between control, cyber sickness, and presence in virtual reality. So now let's look at one of VR's main motivations since VR began. One of its main goals has always been to simulate real life-like experiences. So while some researchers may argue that VR is a medium to dispense totally unreal experiences, people still come in with expectations of how the environment should behave based on real life experiences. So they still expect the virtual world to act and behave in a very lifelike manner. With this being one of VR's main goals for a while, it's still not yet achieved. So what has stopped VR from achieving this goal and taking off as a widely accepted ubiquitous computing platform technology? There's still something that's stopping that from happening. So those barriers have been cyber sickness and the inability of our current technology to generate adequate levels of presence. So cyber sickness is a malady that's caused as a consequence of VR usage. It's similar to motion sickness, and it's got the symptoms such as nausea, eye strain, dizziness, sweating, fatigue, etc. While researchers will argue that current VR technology does generate enough presence, it still comes up that the technology falls short of producing the real life-like experience. So we're yet to be able to see stimuli in the virtual world that actually looks lifelike. So the success of VR as a technology will largely come down to our ability to handle and address the challenges that these barriers pose. Towards that end, we wanted to investigate a factor that relates to these variables so that we could study it towards addressing these barriers. Control, that's the factor we chose to investigate. So why control? Why virtual motion control? So there are several VR applications that have people traveling through the virtual environment controlling their own motion. So this makes it important to investigate this factor. Furthermore, we don't know how it affects sickness or cyber sickness in modern HMD-based simulations. It's been studied with desktop VR and other generic VR mediums, but not in modern HMD-based simulations. And with VR becoming a prominent testbed for user experience testing in the autonomous car paradigm, it makes it worth our while to investigate how virtual motion control affects different aspects of the VR experience. And with virtual motion control, steering is one that's very intuitive, straightforward, and it's ecologically valid in that people come in already having an experience of how driving a car with a steering wheel is. Therefore, it makes it very scalable outside the laboratory. So therefore, we wanted to explore the interrelationship between motion control, cyber sickness, and presence in immersive virtual environments. But we also wanted to study other variables because these variables mesh in well with this aim that we had, because having to drive a car could come at the cost of an increased workload. And furthermore, we had time-related constructs like duration and perceived time. These are important because cyber sickness could affect how long you're able to spend in the simulation, and perceived time and presence are often talked about together because you feel more present when you perceive less time, and the opposite. So it makes it worth our while to examine this interrelationship. This was our broad research aims. And the reason why I provided you with these research aims before I discussed the related work was so that it gives you a context of what our overarching goal was, and to make it more coherent for you all. Now let's look at what the research community has had to say on the relationship between some of these constructs. It's been shown that the affordance of control generally renders people less sick to sickness. This has been shown in the real world, in the virtual world involving virtual avatars, as well as in desktop VR. Dong and his colleagues showed in 2011 that drivers became less sick than their passengers when they played the Xbox 360 Forza 2 racing game. Now let's look at how workload and sickness have been studied in the past. There's work that shows that a higher workload can reduce the amount of sickness experienced, and then there's work that shows that higher workload conditions can increase the amount of sickness experienced by the participants. And then there's work that reports that there's no relationship between workload and sickness. So as such, the scientific community is yet to provide a united position on what the nature, strength, and direction of the relationship between these variables are. Now let's look at how sickness and presence have been reported on concurrently. There's a lot of the work that's suggesting a negative relationship between sickness and presence. It isn't uncommon to hear of positive correlations between these variables, but the number of studies that report a negative relationship strongly outnumber those that report a positive relationship. With regards to cyber sickness and duration have been shown to be positively correlated. So the more time you spend, the more sick you get. And there's also some work which say that there's a negative correlation, and the reason for the negative correlation is because people adapt to the virtual environment. And then there's a community of scientific researchers that claim that people spend more time in the simulation only because they feel less sick in the first place. And now let's look at how duration, perceived duration, and presence have been talked about in the past. It's been shown that the more time you spend, the more present you feel, because you're able to understand, become familiar with the virtual environment. With regards to perception of time, or time perception, there are two ways to measure it: prospective and retrospective time estimates. Prospective time estimates are where participants are told, hey, I'm going to ask you at the end of the VR simulation how long you spent in there, so keep a track of time. Retrospective time estimates, on the other hand, is where participants are not told that they're going to have to estimate the amount of time, and they're just asked to do so on the fly. The retrospective time estimates are hence more ecologically valid in that you very rarely find yourself in situations where you're told that you're going to have to estimate time before actually enduring a simulation. So again, the goal was to study the interrelationship between these variables, and towards this end, we developed a virtual environment that had a 120 block city radius of a city, and it had tall and short buildings all over, and we had miscellaneous objects placed around to reduce monotony with the city. This was the layout we followed for our city, where we alternated between tall and short buildings in a concentric pattern to provide smooth optic flow, and we also distributed landmarks evenly across the city. This was used for a search task, which we'll describe later, and the landmarks were very salient and distinguishable from the rest of the city, and these are some of the landmarks you can see. We had participants sit on top of a Subaru car seat that was mounted on top of a wooden platform. They used the Logitech steering wheel and the acceleration and brake pedals to control the car if they were indeed assigned to a condition where they had to control the car. And they used the HTC Vive Pro and the HTC Vive controllers to provide them with a gender-masked, scaled self-avatar. This is what the first-person POV looked like in the simulation. This brings us to our targeted research question, where we sought to examine how these variables, specifically these variables, were interrelated or are interrelated in an HMD-based driving simulation. And furthermore, we wanted to see how control affects the different aspects of the VR experience. So we developed the following hypotheses based on work we discussed in the related work section, where we hypothesized that control would affect the workload experience, and the workload experience would determine how sick people got, and how sick people got would determine how much time they spent in the simulation, and how much time they spent in the simulation would determine their retrospective time estimates or their perceived time, and finally their perceived time would determine how present they felt. So we designed an experiment, which was a between-subject study manipulating the affordance of control between three conditions: the driver condition and the yoke pair condition, the autonomous car condition. The driver condition and the yoke pair condition formed a matched pair in that participants experienced the same vehicular motion stimuli in both of these conditions, with the only difference being control.
In the driver condition, the participant had full control of the car and could drive around a city as he or she pleased. Their task was to find a landmark presented on the car screen. Once the participant found a landmark, a new one was presented. The task remained the same across all conditions. In the other two conditions, the participant was driven around in a self-driving car with different behaviors. The autonomous car accelerated and decelerated at a constant rate and followed all traffic rules and regulations. Whereas, the yoked pair car behavior was a playback of one of the driver's trajectory from the driving condition.
We also incorporated a search task for participants to perform while enjoying the simulation, and the reason we added the search task was so that they would look outside the car and that we could keep them engaged for longer periods of time and give them reason to stay in the simulation for as long as possible. So we had a total of 63 participants with 21 allotted per condition, and 68% of the participants were males and their average age was about 24 years old. And we found that the VR experience did not significantly differ across the conditions. So this is the procedure of what participants went through. They first consented to participate in the study, following which they filled up a demographic survey, and then after this they filled in the first instance of the SSQ, and then the first 42 participants were randomly allotted to either the driver or the autonomous condition. And the reason that we had to subject the last 21 to the yoke pair condition was because we needed to collect the 21 participants in the driving conditions stimuli so that we could randomly assign it to each of the participants in the yoke pair condition. This made a total of 60 participants. So now let's look at the procedure for participants in the driving condition in specific. So they were first sat down and briefed about what the task involved, and then the Empatica E4 was strapped onto their hands to gather SEL data, following which we measured their arm lengths and strapped on the HTC Vive controllers to provide them with a gender matched scale self-avatar. Following this, they began the simulation, and the simulation ended after 30 minutes or when they said, hey, I'm done, I can't take it anymore. And then they filled out the post-SSQ, following which they filled out a question about their perception of time, and then we got data on their workload experience using the NASA TLX survey and their presence using the SUS presence questionnaire. Now, structural equation modeling allows for us to build frameworks and study the interrelationship between variables. It basically has two components to it: a path model and a measurement model. The path model specifies how variables are linked or what order they're linked in, and the measurement model specifies how well certain items measure a construct of interest. So how well do these 6 questions actually measure presence? And the path model specifies, oh, wait, should this go first or should that go first? Or what's the order of linking the variables? It's based on a priori theory derived from their later work. So this is our final model, but it's important for you to understand how to interpret it. So the asterisks represent the significance levels. The pink box represents our independent variable, and as you know, we've manipulated control in this experiment, so control being the independent variable here. And our baseline we chose arbitrarily as the yoked condition, so the comparisons are driver versus yoked and autonomous versus yoked. The R square within each ellipse represents the proportion of variance explained for that construct, and the red ellipses represent the constructs that were subjected to confirmatory factor analysis, wherein we determine how well that construct was measured by the questions that were set to measure it. The pluses and minuses denote the nature of the relationships, and each line has the regression coefficient and the standard error enclosed within parentheses. Now let's get into this model step by step. Let's first look at how control affected presence. We can see that drivers experience higher levels of presence than their yoked pair counterparts. We can also see that the autonomous car condition felt more present than their yoke pair counterparts. So we think that controlling the car, which meant that people performed interactions with the virtual environment, is probably the reason why drivers felt more present than their yoked pair counterparts. With the autonomous condition, we think that because the car behaved in ways that they'd expect, following speed limits, adhering to traffic rules and regulations, this may have caused it to be perceived as very realistic. Therefore, they might have felt it to be more presence-inducing. Now let's look at how control affected perceived time. We can see that the autonomous car condition perceived the simulation to be the longest. We think that it's because adhering to the speed limits, following all the rules and regulations may have caused participants in this condition to think that the simulation was just longer than the other conditions. Now let's get to the interesting part, control on workload. We can see that drivers experience significantly higher workload. So this is intuitive because we can expect that the drivers could have been more active than their passive yoked pair counterparts, and having to drive could come at the cost of an increased workload. So that's probably why the drivers experienced a higher workload than their yoked pair counterparts. Um, so with drivers experiencing more workload, what does this mean? We saw that workload increased the amount of sickness. Higher workload conditions may actually render people with lesser resources to devote towards handling the sickness-related symptoms, thereby making them more sick. So now let's look at how cyber sickness affects the different aspects of the VR experience. So let's look at the direct effect of cyber sickness on presence. So first we can see that it lowers the levels of presence experience. And this aligns with the majority of work that is supported concurrently on this. And we think that sickness symptoms may cause people to be more internally focused, thereby processing the virtual environment lesser, as explained by Whitmer and Whitmer-Singer in 1998. There was also an indirect effect of cyber sickness on presence through the time-related constructs, which we'll get into right now. We can see that cyber sickness renders people able to endure the simulation for longer periods of time. So the more sick you get, the less time you're able to endure the simulation. As I mentioned earlier, a community of researchers that posit that people spend more time in the simulation only when they feel less sick in the first place. And as Bloch explained in 1978, the retrospective time estimates are positively related with the time spent. So therefore, the more time you spend in the simulation, the more likely you are to perceive that you spent more time. Again, this was significant. And then with regards to the amount of time perceived and the presence levels, we found that there was a negative relationship. So if you perceived more time, you felt less present. And if you perceived less time, you felt more present. So you can think of this in terms of idioms like time flies when you're having fun, or a washed pot never boils. And we also observed a direct effect of cyber sickness on perceived time, wherein cyber sickness led to users perceiving less time. So this was our overall final model. And we can see here that control directly increases presence, but indirectly through cyber sickness and workload could reduce the amount of presence you experience. However, the net effect of control and presence was positive because the strength of the direct effect of control and presence was stronger than any indirect effect. With regards to cyber sickness and presence, cyber sickness does reduce presence directly, and the indirect effect may suggest otherwise through the time-related constructs, but the strength of the direct effect of cyber sickness on presence was stronger than the indirect effect through the time-related constructs. So we can offer the following takeaways from the study. Control is definitely important in addressing the challenges that have stopped VR from succeeding. So in generating adequate levels of presence and reducing sickness. And we can see that affording control can increase presence, but come at the cost of an increased workload. And this increased workload can increase the amount of sickness you experience. So based on this, we offer the following recommendations. Because we saw that the autonomous car condition was not significantly different from the other two conditions, we can safely use VR as a testbed for studying UX associated with the autonomous vehicle paradigm. And we also advocate that VR developers focusing on developing driving simulations try and reduce the amount of workload associated with the travel metaphor. And lastly, we think that it would be very beneficial for the scientific community to measure, analyze, and report workload when investigating sickness. With that, I'd like to conclude by thanking our team. That's me, Rohit, my brother Roshan, and Reza, Matthias, Dr. Babu, and Dr. Kneinenberg. With that, I want to open the floor for questions, and once again, I'd like to thank you all for attending this talk.
Thank you very much, Rohit. It was a great talk. We have a couple of questions coming in right now. And the first one I'm going to ask, given the talk that preceded yours, is for clarity. Is this actually the same experiment with the same participants presented in the previous talk? but evaluating a different set of results.
Correct. It was the same experiment evaluating a set of different results. You're right.
Okay. Let's see, another question. Do you and your brother get cybersick in virtual reality? And what recommendations do you have for people who do get cybersick?
Interestingly, both of us don't get cybersick at all. So we don't know the phenomenon we're studying. We've not personally experienced it. With regards to what we can do to alleviate it, in terms of first aid, you can chew ginger, chew gum, rest, you can drink water, and you can stare at the horizon. Those are recommendations I can give you for immediate first aid relief of cyber sickness.
Okay, so let me ask one more question. And that's for someone not well versed in structural equation modeling, could you explain if there are other effects, say control to duration or workload to presence?
So structural equation modeling basically allows to build frameworks. So when you're doing the structural equation modeling, you actually construct a saturated model where you create effects from every predictor to every successive construct in the model. So yes, we did plot workload to duration and every possible permutation of effects, and we observed that those effects were not significant, meaning that those effects are mediated by the variables in our model. So the model here allows us to claim that it is a flow through these variables.
Okay, so I think at this point we are going to end our session, and I'm going to strongly encourage people to join the speakers and me in the room number 2, large room number 2 for track 1, where I'll have the equivalent of people walking up to the front and actually talking to the speakers. I think there's going to be enough room in there, and if there is not, we'll go over to room 3 as well. We're not going to be in room 1 since it is at least supposed to be recorded. We'll be in room 2 for track 1, and we're signing off right now and hope to see you real soon.
See you guys. See ya.
Bye.